Alrighty, hello everybody. Welcome back to Jensen X Space. We've got some new research that's recently been published and also accepted into the ICML conference, which is fantastic. Welcome to Eros Fani and Og, Ersoy. Eros, the lead author on this paper, IR3DE, a linear router for large language models. Gentlemen, welcome.
Hey, Xavier. Thank you for inviting me once again. It's a pleasure to be here and present IR3DE to everybody.
Absolutely, a pleasure to have you. Ozzy, how are you?
Hi, Xavier and everyone. Indeed, it's really nice to have everyone here and talk about our latest research.
Absolutely. I'd love to get straight into it. Eros, you're the lead author on this paper. Why don't you give us a quick rundown on what IR3DE is, what you were trying to achieve, how you got started in this particular angle of research that resulted in IR3DE.
Of course. Yeah. So the idea is say that we have like a pool of different expert models. Let's say like we have math expert, biology expert, coding expert. It's not like important where they are. So it is like this work is suitable also for decentralized settings. I will explain much better later on this. But suppose like for now we just have these experts. These experts are typically like very large language models, and like you don't really know the prompts that you submit to these experts if they are the most suitable for each of these experts, right? What we were looking for is like a method to dispatch the prompts automatically to the best suitable expert on the available pool without this method being too complex or too costly, because otherwise it was just being like I wouldn't say like the same, but like not optimal, because like otherwise you you could just prompt each of these experts and pick the best solution. That is not what we want, right? Because like forwarding through a whole LLM is a costly process, and it's just much better to pick the best expert every time and forward your prompt to the best one. Of course, like it's not a problem that we invented. It's a problem that has already been investigated in the literature. The main contributions that we add here is that our router is very cheap to be computed and can be computed in a decentralized setting and in a modular way, in the sense that if you already computed it and there is a new expert coming in the pool, you don't need to recompute the router from the very beginning. You just update the router from where you were before, right? And also like it works also in the other way around. So like if there is like one expert that leaves, you can just remove its contribution and the router works as it worked before. And like one very important aspect, you don't need to do any gradient-based training. So like there are other methods in the literature that use additional language models to do this routing process. For instance, like there are methods that use an additional BERT or the Bertha model, which are not like huge models, but still they are quite large models, and you need to do training over them to make them work. It's not something that you need with IR3DE. So I would say like these are the things that we bring with this router. And yeah, this is like the pitch. So do you have any question? Like I can also go over how it is constructed if you want.
We will get there very shortly. Yes, I'm very glad you pronounced it for me as well. IR3DE. Is that what we're calling the acronym there?
Yeah, like it's the way I read it.
Fantastic.
Actually, it comes from like I mean, I'm Italian. There is like an Italian word. IR is just like the core part of the eye. So the idea is just like for me, like the way the reason why I named it like this. It is because like it's I mean, it's more like if the router allows you to really see what is the best expert model for you. So it is like alpha wave between an acronym and the real I mean, and this abstract concept that I had in mind, but it's just like yeah, I like this name. Ozzy liked this name, so we decided to keep it. For instance, like the R3 is because it is a ridge regression based router, so there are 3 Rs there. The E is because of inference, although like we didn't mention it because like it's not like in the literature people don't call this a typically inference router, but still you use this router at inference time, so like it's something like that. But anyway, let's maybe talk about how it is constructed.
I like it. You did mention that in the literature, when people have been discussing working on similar problems, methods that were suggested, it sounded like they simply required more effort, more time, more cost, and IR3DE actually reduces all of those things, so you get to your expert, to the best expert, a lot quicker. Is that a reasonable summation?
Yeah, exactly. So the point is like there are some other methods. I can mention like a couple. So there is like KNN from Polyrouter. There is another one. It's called Modem. So like in this Polyrouter paper, they propose like several types of routers. They didn't pick one. They say just like, okay, there are these routers. This is better in this case. This other is better in this other case. But all of these routers, what they have in common is that they use this BERT model to construct like embeddings of the prompts, of the entire prompt. So like, let's say you have like this whole sentence. To process the sentence, you cannot use it as it is because it is made of characters, right? You need to add vectors to make it processed by an LLM. This always happens also in standard LLMs. Like when you talk with ChatGPT, there is a conversion inside happening. There is doing an embedding, but this embedding typically is an embedding that is happening token-wise, while what they wanted to achieve is an embedding prompt-wise. So which means like you have this prompt and you want to have a latent feature vector, okay, that somehow represent the domain of the prompt. So let's say like the domains, as I said before, like there are math, biology, and coding. You want to add this vector that somehow discriminates between math, biology, and coding. The problem on the way these methods like the polyrouter and modem did this is that just that they trained another model that is not small, neither, I mean, it's not large, but for sure it isn't small, okay? They needed to train this, and this model to have these embeddings to encode the prompts in a meaningful way. And the fact is that if you need to do this training, you also need to collect the data somewhere or do complex coordination strategies to make training work in the centralized settings. While with ridge regression, the people, I don't know if here there are people that attended also like the other X-Space when we talked about Doom. The idea is very similar. So with ridge regression, you can actually, I would say like very simply divide these contributions of the single data set. So let's say you have a data set of math, a data set of biology, and the data set of coding. You can construct some statistics, and these statistics can be constructed in a decentralized way. And then you can just collect a couple of matrices that are these two statistics, the two statistics that you need to construct. You collect them, and basically from there you do some linear algebra and find a router. And then I can explain how we use it because it is only one ingredient of the whole IR3DE router. But yeah, so this is the general idea. And the point is like with IR3DE, you don't need to do gradient-based training. Especially the point is you don't need to do forward and backward passes through a medium-sized model. And you can construct this in a decentralized setting. The construction is modular. You can add and remove statistics the way you want, and this is perfect for the centralized setting, I would say.
Fantastic. Ozzy, I know you were contributing to this this research as well. What's your take on the wider benefit of IR3DE to the industry, to training, to research in general?
Yeah, Eros actually quite well explained. So right now we have quite a few generalist models that are quite large, and people are using like Swiss knives, which are including like a different task, like you have a general maybe chat question, or you have a simple math question, or you want to improve your code, then you use this very large model that's kind of trying to answer all at once. Even though these generalist models, they are decently well in each different tasks, they have some drawbacks. One of them is like, since they are quite large, even though you have a very specific task or expertise that you require, you still need to run this whole large model to get your output. So it's costly. And at the same time, since these models are quite generalist, so they are not excelling at these specific tasks. So for that reason, for the efficiency of the generation, it's better to use an expert model for the task that you wanted to achieve. Like in the case of coding, for example, it's better to use a coding model because it's specialized. It does more efficiently achieve what you want to do. But the caveat with that is that like sometimes you may not know which model that you want to use, or you don't want to like regularly manually switch from a coding model to a math model, or I don't know, maybe you might have a model on medical data or domain, or you might have a model on multilingual domain. So you don't want to manually switch between the models. So for that reason, we have these routers. So router is basically automatically looking at your prompt and then analyzing, okay, this prompt is more suitable for this expert or that expert. So by doing so, you can significantly improve the efficiency of the generation. So this is generally the advantage of the router. And our work is among the router space has two advantages. One of them is the efficiency, which is as Eros mentioned, our router is like very small. So it is very easier or cheaper to calculate which model to send your prompt. And another advantage is that it has this asynchronous dynamic router construction. What do I mean is that imagine that we have three models, let's say math model, a code model, and general chat models. We might have a router that decides on which of these experts to send our prompt. But later on, maybe there's a new model that's developed on medical data, let's say, and we want to integrate that model to our router. The existing routers, they work in a way that like they look into all these experts as a fixed set of experts, and then they try to optimize the prompt based on this fixed set of experts. So whenever you add or remove an expert, then you need to retrain this router. Whereas in our case, since it's basically a very simple linear construction using ridge regression, you can easily add or remove experts. So that's also one of the advantage of our system, which is also quite suitable in a decentralized setting, because in a decentralized setting, there would be more dynamic serving of the experts and additions or removals of new experts. So you don't want to retrain the router every time you want to change the expert models that you want to use. So with our construction, it's quite simple to do it without needing to do the retraining.
Fantastic. As Eros was saying, quite a modular setup of adding and removing and plugging and playing to a certain extent with each expert.
Exactly.
Marvelous. Eros and Ozzy, feel free to jump in as well. Where do you see the biggest benefits to Jensen, to industry? Where is Editor going to fit in the future, and how is it going to improve things for anyone dealing with LLMs?
Yeah, the benefit to me is very clear. So as Ozzy said, like if you have like generalist models that are typically very large models, they may be like good in solving like any task. Like let's say we are just assuming like there are like math, biology, or coding tasks in the examples that I made during this talk. But like you can have more, of course. And I think like everybody here tried using Claude or ChatGPT or whatever LLM they prefer. So the point is, if you need to do, I mean, to interrogate like LLM sequentially for like very complex tasks, or you have like very niche topics, and you, for this reason, you need experts that are small, fast, maybe not that small, like I would say smaller than I don't know, like Opus 4.8. Okay, if you are like, you need to systematically use expert LLMs. These LLMs don't live in the same host. They, for instance, are in a decentralized environment. With our IR3DE work, you can solve this, and I can already anticipate you that we are working on a practical decentralized version of IR3DE. Yeah, I can tell you just this for now, but we are on it, and yeah, the idea is more like, and everybody just communicating in this decentralized network. They communicate the statistics, and with them they can construct the router and automatically pick the expert in the network that is more suitable for the prompt. And in this way, given that like people are constructing their own routers locally, they don't even need to like trust other people, right? Because if you don't like one expert, you just say, okay, I don't want to pick this expert anymore. I don't need to trust another person, another host having like its own router. Like let's say if like there is another guy hosting the router, maybe I need to trust this guy to be fair, right? But if like you let people to keep their own routers, that is much better, because like you trust yourself. So yeah, you remove this problem entirely. Yeah, so to me, like the idea is you having this setting, you reduce the dependence on generalist models, and we are able to imagine like in the future a network with several hundreds or even thousands of nodes that are like making their models available, and they can be queried by other users. There could be like the nodes could be like even both requesters and providers of the model. So yeah, this is my interpretation. I don't know if Ozzy wants to add anything on that.
No, I totally agree. Especially in a decentralized setting where you want to add or remove expert models, or you want to have a more dynamic network, our router is basically providing a much simpler or cheaper solution, because it's very straightforward to add or remove experts without necessarily training the whole router. And since the router itself is just a linear function, it can also stay locally in each user. So that makes it also more suitable for a decentralized setup, because now everyone can say that, okay, I want to use maybe this and that models only, so I want to construct my own router. And because the way that we construct the router is basically using the vector statistics from each model, each user can just, by picking the models that they want to use, get the statistics from the corresponding models and then construct the router for themselves. So everyone can have their own version of the router based on the models that they want to use.
That's marvelous. That's the point I've been rolling around in my head since Eros mentioned it earlier on the decentralization, running your own router, the trust issue, plus all this variety of models that you can use. Is that absolutely any model somebody could plug into it, or are there some restrictions?
Well, basically, our router construction requires each model to provide some statistics, but it can be it can be any model. So there's no limitation that prevents some of the models to be part of the router.
Yeah, I maybe add only one thing about this. So like the thing that is required is that the statistics are extracted by using the same embedder. So what the way we do it is like we for every token we extract the corresponding embedding vector of the token. This is like could be like literally any embedding token embedding layer of an LLM. The only requirement for now is that all the hosts need to use the same embedder vector just for the sake of extracting these statistics. But apart from that, they can use any other model they prefer. Not any other model they prefer. Like, let's say you declared you have this model, you should be stay with that model. But apart from that, you can use even another expert, as long as this expert is an expert of chemistry, biology, or whatever. Okay, so the idea is as long as all the models use the same embedding layer, then you are fine. So this is the very only requirement. Maybe in the future we will work also on some translation mechanisms to, like, for instance, if like there are hosts that use different tokenizers or different token embedding layers. Okay, maybe we know that there are like techniques that allow you to translate between one to another. So maybe we want to also plug in these methods. But let's see. Like this is not something that we are currently working on, but it's something that we are pondering if we would like to continue on this on the future.
I love it. The questions, the possibilities, they never stop. I'm running around in my head some fairly clear links to some of the talks we've had recently. Johnny was up here not long ago speaking about diversity of models. And Eros, yourself, the first time you were with us was around the mixture of experts topic. Does this have much relationship to that mixture of experts work that you were doing?
Yes, absolutely yes. Like the core technique that we are using. So like for IR3DE, I actually have just mentioned how we construct the router, but not how we use it. But the way we construct the router is almost the same as the way we constructed the mixture of expert routers that are actually a different concept. It's not the same as in here. So like maybe I give just a brief introduction of what mixture of expert is, because like for people that don't know.
Go ahead.
So like mixture of experts models are like just like normal LLMs, but like LLMs are typically made of transformer blocks, and each transformer block is made of an MLP, a self-attention layer, and then there is an MLP layer, right? So there are works showing that instead of having this structure, you should have instead of having just the self-attention and one MLP, you should have one self-attention and several MLP layers, which would be several blocks of MLPs, which could be even like 3, 4, 5, and this should be like distinct blocks in a way such that you can train the model in a way such that like the different expertises depending on the token is gonna be encoded during the training in each of these different experts. This is like in a very short how it works, and the only thing that you need to look more closely, more carefully, is like how you do the routing. So when you forward to the self-attention, then you need to decide for every token to which experts, in the sense of the mixture of experts blocks, you want to forward your tokens. Okay, so actually, like mixture of experts are born to allow people to enlarge their the size of their models, like to allow it to achieve better performance without enlarging too much the number of parameters of your models. So this is the reason. It's just like a cost reason. But then there are like works that show that you can actually do the things the other way around. So let's say you have already expert models and you want to combine these models. Okay, you can just do the average of all the layers, but the MLP layers, you keep the MLP layers separate, and you treat these MLP layers as different mixture of experts. And then the problem with existing methods was that you needed to add a router to pick the most suitable the most suitable expert for every token every time. And the way that existing method did this was just by doing additional training over the whole model, just to train the router, right?
Right.
Which sounds like a weakness of the of the overall construction. So what we did was like applying ridge regression in a very similar way that we did with IR3DE, okay? But here the perspective is very different. Here we have different, in this work in Doom, we have different experts, and we want to combine these experts to have one single expert, because you don't want to deploy all the experts. While in IR3DE, we are not interested in combining the experts. We don't want to do any training. We want just to do inference over these experts. And the way we do inference over these experts is by picking the experts, but the experts remain separate. So like we are showing actually like in a certain, from a certain perspective, you can, we can say that we are showing how these techniques, this technique, like the ridge regression, could serve both purposes. One purpose is like having one multitask expert without doing any additional complex training. And the other is, how can I understand which is the most important expert for my prompt? So we are literally showing how we could use, we could make advantage of these techniques for both reasons.
Fantastic. Thank you very much for that. Ozzy, I think we've got you back. Up here now, is that correct?
Yes, sorry, I missed the last point.
Just checking. As quite a comprehensive explanation from Eros there on the uses of this router. Just before we start to wind up, I wanted to see from your perspective, which can be slightly different to Eros's, if you had anything to add to that. Oh, he's gone again. Never mind. That's okay. Look, we are just about at time, so I think we should.
Yeah, maybe like
yes.
In the meanwhile, if you want, Xavier, I can also like give you like an idea on how we actually use at the end the IR3DE router.
Please
because
do.
we didn't talk about this yet. So yeah, the idea is very simple actually. So like we said that we constructed this token router using the embeddings that we extract from each token. The problem is that this token router, and which we construct, by the way, using ridge regression, as I mentioned a couple of times yet already. So yeah, the idea is like at inference time, what we do is we transform our prompts in tokens, we do the embeddings, and then we use our linear layer that we just constructed to extract softmax probabilities for each token. What does it mean? These softmax probabilities give you like a distribution on which is the domain that is the most likely domain for that specific token. So let's say that you have the word math, okay? It's very likely that the math word is belonging to the math domain, right? If you, for instance, like you assume that you have math coding, biology and chemistry, you have the word math, or you have like the word sum, I don't know, the word average or whatever. I'm talking about words, but these actually works with tokens, but like the concept stays the same. So these words are very discriminative in the sense of which are the final domains you should forward, the final experts you should forward your entire prompt, right? So we let almost all, like not almost all, like we let some of the tokens cast a vote on which is the final domain of the entire prompt. And the way we do like this filtering of the tokens that should cast the vote is via a top k smallest entropy. So it's not like very important what this is, but the idea is like if there are tokens that are uncertain about the prediction, so like maybe you have the token the, or the token of, or the token to, or like whatever stop word you may think about. So these words, of course, like may appear in different domains, right? So if you have like a prompt that belongs to biology, a prompt that belongs to math, you can definitely have the word the in both and in several prompts. So this is actually great because like our ridge regression suffer from this, and it gives you like very undecided predictions about these tokens, and we take advantage of this because given that we have these undecided predictions about these tokens, we can filter them out and we can say, okay, I care just about the top 10, like the top 20 or whatever number you prefer, the top k tokens that give you the most confident predictions. And then we look at these predictions and pick the majority voting across them. And this majority voting gives you the final domain of the prompt. And we actually found that this works very well because like we made some ablation study in our paper where we found that if you use a k that is too small, which means like you let only 1 or 2 or 3 tokens decide which is the overall domain of the prompt, we have very low routing accuracy. If we have too many tokens participating in the election of the final domain, you still have very low routing accuracy. While if you had like the right numbers, like in between, so between 10 and 20, sometimes 100, but not more than 100 tokens participating in the election, you have the best routing accuracy, which means like that our intuition was correct. And I think like this is very interesting part of the paper, to be honest. Like we added this in like later just to improve like the results, and it actually worked very well based on a very simple intuition that we had. Yeah, so I wanted to like give you also an overview on what our routing, on how our routing actually works at the end.
Oh, absolutely. Thank you for that. How did you actually come up with that intuition? How did you come up with that method? Because some of it actually reminds me a little bit of cracking ciphers in World War II.
I don't know. To be honest, I don't know if there is like any correlation with that. But yeah, I thank you for the comparison. Anyway, like yeah, the intuition was like, I mean, it was more like, okay, we weren't satisfied with the results that we had by letting so like the very first thing was, okay, we have a way to make each token predict a domain, but what we do with the predictions of the tokens, right? And actually the answer to this was quite simple, because like the most natural way was to let these tokens vote in majority voting, right? So like the domain that has the highest number of votes wins. So I think that this is quite an easy intuition. There's nothing exceptional in this. It's very natural. It was very natural for us. But from there, it was actually like much harder to understand, like that we didn't have to let all the tokens vote. And like I mean, we started like thinking, okay, well, but we started looking at the prompts from different data sets, and we say like, okay, there are several tokens like that are appearing multiple times. So maybe like we shouldn't allow them. But the problem was like, okay, how we find these tokens automatically, because we don't want, of course, to over engineer the things, like saying, okay, just exclude these words, because like otherwise, like I don't know, like it is really data set dependent, right? So it should be a method that is automatic. And then I looked more closely to the softmax predictions, and I observed these patterns. That is like there are some words that appear several times in different domains, and they have like very undecided probabilities, very uniform probabilities across the domains. And because of this, then I also did the math to check if it was true, and this was true also in theory. And so yeah, then I just said, okay, we can detect this with the entropy, and we decided to add the entropy selection method at the very top of the algorithm. So yeah, was literally the very last thing that we added to the algorithm.
Maybe one thing that I can add, since my background is on cryptography, so I worked a bit on those topics. So as you pointed out correctly, this is somehow relevant to the frequency analysis, which has been used for World War II or in the following maybe cryptographic mechanisms to detect and break the systems. So in a way, we are also using some sort of frequency checking, where we are basically trying to match the token frequency of some tokens with the domains. So for example, if the token is relevant to, I don't know, derivative, then it's relevant to the math domain, and some other talks like gene is relevant to the biology domain, etc. So this like frequencies of some of the domain tokens are matched with the specific domains. But as Eros mentioned, like we cannot just average each token with a domain, because some of the tokens or some of the words, let's say, appear in every domain almost equally likely. So it's better
Right.
to look into the tokens that are more specific or unique to each domain. So in a way, like we are trying to find the frequency, but we are trying to look into those frequencies such that a token is more appearing in one domain but less in the others, so that it's not also causing a confusion for the router. So basically, our type K entropy method is just looking into these tokens and like trying to find the domain specific tokens. And then once we have this subset of tokens, then we can, by doing the majority voting, we can select the correct domain of the prompt.
Fantastic. Oh, brilliant! Thank you both so much for taking us through that. It's yet another fascinating topic, and congratulations as well, Adu, as the paper has been accepted to the Adapt FM workshop for presentation at the ICML conference in July over in Seoul. So congratulations again there.
Thank you very much, Xavier. Of course, it was a pleasure to be here once again, second time for me, and I really look forward for next time.
We will have you back up very soon, I'm sure. As we're about to wrap up for either of you, have you got any? If you wanted one thought to be taken away from this work by people, what would that be?
Well, yeah, this is a great question. One thing is, we already said that, but I think it's good to make it even more clear than this.
No problem with reinforcing it.
Yeah, so like it is this method is actually, it differs from existing methods in a way such that it is lightweight, it is modular, and it allows seamlessly to add or remove experts at any time without doing everything from the very beginning, which is not something that you should, that anybody should take from granted in any kind of machine learning algorithm, I would say, because typically when you do training, you have so many issues when you try to add like more data that is like on a different topic domain, or you have like other labels, you have to deal with catastrophic forgetting, or even like if you have all different types of data, you have all together, you need to deal with multitask training. Like I know that maybe I'm divagating a little bit, but the idea is that every time you can show that you have an algorithm that is modular and doesn't allow you, it allows you to add or remove things without doing complex methods or like over engineeristic things to like retain the past knowledge, or like to be equally good on every domain or on every whatever you have. Like if you, I don't know, if you're doing other tasks, it could be like different tasks, but like I think that this is a very strong point. So I would say like maybe two keywords that I would bring back with me from this talk are lightweight and modular, and probably also decentralized. Yeah.
Fantastic. Ozzy, what was your thought?
Well, Eros really well explained, so there isn't so much for me to add. Maybe one small thing to add is that since it's decentralized, modular, and very cheap, it's very suitable for a personalized and local systems. Like local in a sense that the router is local, but the models and experts live in a decentralized dynamic network.
Amazing. Thank you both so much. It's always a pleasure having you on. And thank you, everybody that spent their Friday afternoon or morning with us today. Keep an eye out for the next one. We've got a few topics queued up, and we will speak to you all again soon.
Thank you very much, Xavier.
Thank you.
See you.